All right. Mock exam 3 time, I guess. All right, let's get started. So, an unknown noble gas is stored in a 10-liter container with a pressure of 1 atm and a temperature of 273 Kelvin. That's STP, if you guys didn't remember. Um, if the sample weighs 17.83 grams, which noble gas is this? Uh, so this is basically just you're given a volume, a pressure, and a temperature, and what equation do you guys know that relates all of those? It's going to be PV It's going to be everywhere on this test, I think. Um, so this implies that N is equal to PV over RT, which is going to be 1, 10.08, 206, 273. And remember, we're going to use this version of R because we're dealing with atmospheric pressures, and obviously we want that to cancel. Okay, so doing that calculation, 10 over 0.206 times 273, which gives us 0.446 moles of this gas, and then we know that the, I guess like the big determining thing that we use a lot in stoichiometry is the molar mass. And we know that the units for that are grams per mole, so we can just do 17.83, which is our given, grams per 0.446 moles. And then this will give us 39.943 grams per mole, which if we look at the periodic table, that is going to be argon gas, and that is answer C. Which gas sample has the smallest volume at a temperature of 75 Celsius and a pressure of 0.9 atm? Okay, so another question relating temperature and pressure and I guess volume and everything like that. We're again going to be using PV equals nRT, the ideal gas law. Um, okay, so we know that pressure is going to be constant. Temperature is going to be constant. The R is going to be constant. So we know then that the volume is going to be not equal to, but volume is going to be proportional to moles of gas. So if we're looking for the smallest volume, we want the smallest number of moles, and we know the smallest number of moles is going to be whichever gas is the heaviest in molar mass, just because these all have the same masses. So we know the gas with the largest molar mass will have the least number of moles. And then if we look at the periodic table, neon's molar mass is 20.1 grams per mole. Krypton's is 83.79 grams per mole, and argon's is 39.948 grams per mole. So we expect the answer should be krypton because that should yield the least amount of moles. But we can just do the stoichiometry for all three of them just to make sure everything checks out. So if we start with neon, we have 5 grams of neon, and then remember to convert to moles. We divide by molar mass. So that's going to be 20.180 grams per 1 mole. It's going to be 0.247 moles of neon. And then if we do the same thing for, let's just do argon first, just so we don't have to, or just so we have to do all of them, and all right, so 1 mole. And when we're dividing by the molar mass of argon, we get that's 39.948 grams, which is equal to 0.125 moles of argon. and then you can kind of see what's going to happen with krypton. Uh, since it's the heaviest, you'll have the least amount of moles. 1 mole, and the molar mass for krypton is 83.798. So if we do that, that will give us 0.0596 moles of krypton. And remember how we saw, I guess this, for every scenario, volume is going to be proportional to the amount of moles of gas in that container. And if we want the smallest volume, we want the smallest number of moles, and that is obviously krypton, which is like 5 times less of a mole amount than this one, and around half of this. So we know the answer is going to be B, krypton. Okay, so number 3. An ideal gas is in a sealed container with a movable piston to keep the pressure constant. The gas has an initial volume of 10 liters at a temperature of 10 Celsius. If the gas is heated to a temperature of 150 Celsius, what would you expect for the final volume? And so for these problems, this is pretty obviously asking you for like the relationships between certain variables like volume and temperature, or pressure and temperature between two different gas samples. Um, and you can remember the laws, but that's kind of annoying and cumbersome, and I don't really like to do that. So what I do is, and you can also do as well, I set PV nRT equal to PV nRT, and then you just cross out whatever is constant. So we know in this problem we're only looking at volume and temperature, volume. So we're only looking at those. So not changing pressure. It even says pressure is constant. So you can cross out that from both sides. Not changing the mole amount, and R is never going to change. So then you're left with V1 T1 is equal to V2 T2. Okay, and then we're looking for the final volume. So I kind of treat this second side, this whole side, as the final part. So then if you want this final volume, you isolate V2, and then this also implies that V2 is equal to V1 T2 over T1, right? Because we just multiplied both sides by T2. And then we get this, and then this is just as simple as plugging everything in. But remember that when we're dealing with any of these laws, you have to convert everything to Kelvin. So yeah. So the initial volume V1 is 10. T2, the final temperature, what we changed it to, is going to be 150 plus 273. And the initial temperature, T1, is going to be, what is that, 10 plus 273? Okay, yeah, and then once we do all that math, V2, let's just go over here. V2 should be equal to 14.94 liters, which is approximately answer choice B. All right. Accidentally made a mistake on this problem, so I'm just gonna restart it. Just realized that after recording everything. So a gas cylinder contains a mixture of N2, O2, and CO2 with partial pressures of 0.6 atm, 0.92 atm, and 0.38 atm, respectively. If the cylinder contains 5 total moles, how many moles of N2 do you have? So the main big equation we're going to be looking at here in the relationship is that chi of anything, which is just like a fraction of things, I guess, in a container for gases or moles of gases, you're going to get the moles of A over moles total is equal to chi, and also that the partial pressure of A over the pressure total is equal to chi. So you can use these to your advantage that, well, we're trying to find the moles of N2, but I mean, we weren't given that. We were only given the total moles. So what we can do is that chi of A is equal to, or I guess in this case, chi of N2 is equal to moles of N2 over moles total, which is going to be the moles, oh my goodness, we're using partial pressures, pressure of N2 over pressure total is equal to, and the pressure of N2 is going to be 0.6 over the total is 0.6 plus 0.92 plus 0.38, which is going to give you a chi of 0.6 over chi of 0.3157, I guess. And there's no units for this. This is just like a fraction quantity for this container. So if that equals that, if we use this down here again, we know that chi of A is equal to, I guess in this scenario, chi of N2 is equal to moles of N2 over moles total. And we can rearrange this to solve for the moles of N2. And we get that moles of N2 is equal to this chi of N2 times the moles total, which we're given. And then if we use this 0.3157 times the total moles, which is 5, we get 1.57 moles of N2, or 8, I guess, since they rounded up, and I didn't include that many decimal places. Yes, answer B. Number 5, lithium reacts with nitrogen gas. According to the reaction, 6 moles of lithium plus a mole of nitrogen gas creates lithium nitride, I think. How many moles of lithium react completely with 0.585 liters of N2 gas at a temperature of 300 Kelvin and a pressure of 0.92 atm? And this is another problem. You guys should be able to just kind of know that it's telling you to use the ideal gas law whenever you have 3 variables from that equation and you're trying to find the other one. So we set up PV equals nRT, and we're given volume, temperature, and pressure, and we're trying to find moles. And right, that makes sense because we're given numbers about N2, but we want to find things about lithium, how much lithium, how many moles of it needs to react with that much nitrogen gas. So then this implies that N is equal to PV over RT is equal to, just plugging in all the numbers, pressure 0.92, 0.585, 0.08206. Again, using that R constant, the universal gas constant, because we're dealing with atmospheric pressures. And then temperature is already in Kelvin. Really nice, I guess. Okay, so plugging all those numbers in, we get 0.0218 moles of N2. And then this is just like on the last test, how we had to use the internal mole ratios in the equation that we're given to solve for something else. It's the same exact thing. So start with your given, which is what we just found right here. So 0.0218 moles of N2. And then we're going to multiply that by something to cancel those moles of N2 out, and then find what we want, which is the moles of lithium. And looking at the equation, the things that relate them are the stoichiometric coefficients. So for every 6 moles of lithium that react to form the 2 moles of lithium nitride, you also need 1 mole of nitrogen gas. So if we want these moles of lithium, and we have this N2, we want to put this moles of N2 on the bottom. It's like in math where you have x over x and that cancels out and you just get equal to 1. That's the same thing's going to happen here. So we have, in this, the coefficient here is going to be 1 in front of the N2. So 1 mole of N2 goes along with 6 moles of Li, of lithium. So that's just multiplying the moles of N2 by 6. And then you get 0.131 moles of lithium, which is answer choice D. Which of the following statements is incorrect when assuming a gas is ideal? So, okay, yeah, this is another good thing to know. gas molecules are widely separated from each other, and that is an assumption we make whenever gases are ideal. We assume that they're widely separated from each other and they have no appreciable attraction between each other, and that I think the average kinetic energy is related to the temperature. I think those are the three assumptions. So if we look at these, you see that for the first one, gas molecules are widely separated from one another. What was the question asking? Which of the following statements is incorrect? Okay, so we're trying to find which one of these are not the assumptions we make. Um, so can't be this one. Each gas molecule in a pure sample moves at the same velocity. That's a possible one. And then gas molecules occupy negligible volume. Another assumption from ideal gases is that they don't take up any space, so probably not that one. Gas molecules move with an average speed that depends on the temperature and molar mass. Probably not that one. So I mean, you guys probably already know it's going to be answer choice B. Um, and you guys actually, I guess, not really prove this, but um, we saw distributions of it in class, the Maxwell-Boltzmann distribution of gases, and this answer choice B says that each gas molecule in a pure sample moves at the same velocity, and we know that's not true because we've seen the distributions, right? And we know that it's going to look something like this, or something like that, and this is going to be speed on the bottom. So we know very obviously just by reading the axes that that's not the same speed. They're spread out, so can't be that one. And that is the incorrect assumption. Oh yeah, look, it's just what I wrote. Which one of these gases in the graph below has the largest molar mass? Assume that all four gas samples are at the same temperature. And this is, I think, from that same worksheet with this thing. I don't know if you guys remember, but this is the V RMS is equal to square root of 3 RT over molar mass. So yeah, you guys know that not even looking at RT, V is going to be proportional to 1 over the square root of molar mass, which means that as molar mass increases, this speed is going to decrease. So if we look at the graph, which one is, I guess, mostly from like the peak is kind of where I look at the lowest speed. We see that it's just D, and that is answer choice D. Yeah. And another side note, whenever you're using this equation, this is, I think, one of the few times where we do actually use the other gas constant. So this is going to be 8.314 joules per mole Kelvin. And then another side note, another important thing, because this will like ruin your answer. This molar mass is going to be in kilograms per mole. So molar masses on the periodic table are given in grams per mole. So you just need to divide that value by 1,000, and you'll have your molar mass in kilograms per mole, because there are 1,000 grams in a kilogram. Okay. Of the situations given below, which ones imply that delta E system must be negative? Okay. So delta E system is negative whenever whenever the system does work on something, right? It's like, you can think of it as like, if you push something, you're expending energy, and energy is going to be leaving your body. And then the other one is heat leaving the system, right? Because heat is energy, and if heat leaves something, then it's going to be a negative energy change. Okay, so for the first one, work is done on the system. So we know that work done on the system means that the system is going to be gaining energy. So that means, for at least for this part of the problem, that delta E is going to be positive, and then heat is gained from the surroundings. That's also like gaining heat, gaining energy, kind of synonymous with each other. So that's also delta E is positive. So it can't be that one. You can automatically cross out anything with 1 in it. So that's A and D gone. Okay, and then work is done by the system, like we just said. If work is done by the system, you can think of that as like lifting weights or pushing something. You are expending energy, so you're going to be losing energy. So we know For this one, delta E is going to be negative. And then heat is lost to the surroundings. Heat is lost. That means energy is lost. So delta E is also negative for that. So we know that for answer choice 2 right here, this is for sure going to be in the answers, or going to be in one of the answers. And then if we look at scenario 3, work is done on the system. So we automatically know work done on the system again. That means delta E for that portion is going to be positive, and heat is lost. That means delta E is going to be negative. And it's just like in the worksheet in that one question where you had to answer a similar scenario, and it was going to be indeterminate because we don't actually know the values of these. So we automatically have to rule it out because the answer says implies that delta E must be negative. This third scenario might be negative, but not necessarily because we don't know the values. So that means I need answer choice with 3, and then that leaves us with answer choice B. Which of the following, with specific heat capacity provided, would show the smallest temperature change upon gaining 200 joules of heat? Okay, so I think this is on one of our most recent worksheets, but and I left it on feedback on some people's homework. But so the heat capacity, which is kind of the only thing that changes, like you can have, if you're considering Q equals MC delta T, the only thing that's going to change if you have the same mass and temperature change for all of them is going to be the specific heat. And specific heat I kind of think of it as like a resistance to temperature change. So if you have a large specific heat, then you'll resist that heat change or I guess better, so you'll change temperature less. That's kind of like a good quantitative thing to think about that, because that might be on the test, who knows. But for this problem, it gives you the mass, and it gives you the heat change. And then this is also gaining, so that's going to be a positive Q right here. So I guess what I would do on this is automatically start with Q equals MC delta T. I would arrange this for temperature change, because that's what you're looking at. Temperature change is going to be equal to Q over MC. So we know if this is constant, this Q right here is going to be constant. We can kind of think of that as like crossing it out, and we can imply again that delta T is proportional, not equal to, but proportional to this mass, or 1 over mass times 1 over the specific heat. And at that point, we're just looking at which one of these products of mass and specific heat will give you the largest number, because right, if these are inversely proportional, if one of them is large, the other is going to be smaller. If this increases, this is going to decrease, just like we had in that problem a few problems ago. So we want the largest product of mass times specific heat. And if we look at this, we can already cross out from these scenarios C and D. We can cross out C, because this is going to be, C is going to be 50 times 0.128, D is going to be 100 times 0.128, so that's automatically twice as much. And then we have to look at and then we have to look at A and B, and then we can also automatically cross out B from these two sets, because they have the same mass but different heat capacities, and we know this one is 3 times larger, so that'll be a 3 times larger product of mass times specific heat. So then at that point we can just compare these. So for this top one, it's going to be 50 times 0.993, 50 times 0.903 is equal to 45.15. And again, this number right here doesn't really mean much. We're just kind of comparing them, like we said, because we reasoned over here. We want the largest product. And then for this one, it's going to be 100 times 0.128. I mean, you guys can probably already tell which one the larger one is, but it's good to get practice in. And this is going to be 12.8. And then this is way larger. So if we want the smallest temperature change, then the answer choice is going to be A. Okay. 150 milliliters of a zero point 0.2 molarity HCl was added to 150 milliliters of a zero point 0.2 molarity NaOH in a styrene cup. The initial temperature of both solutions was 25 Celsius. The final temperature was 27.1 Celsius. Calculate the delta H of reaction. Okay. So, and it also gives us that, or it tells us to use the correct sign of the heat, gives a specific heat, which is just water, and the density of the solution. And we just did this in class today as an example, but you can kind of think of this, so it gives you two solutions. You can kind of think of this as just like adding both solutions together because you're mixing them. This is going to be 150 milliliters. This is another 150 milliliters. So the total is going to be equal to 300 milliliters of solution. And because we're doing a coffee cup calorimetry thing and pressure is going to be constant, I think that's what that was. But because there's some assumption we make, I forgot, but I think it's that pressure is constant. But you can say that in this scenario for coffee cup calorimetry, Q of the reaction is equal to delta H of the reaction. So we can't really get this properly unless we know, or unless we have like delta H of formations or bond enthalpies or whatever. So, but we can use this, and we know that Q is equal to MC delta T. And we have the temperature change, we have the specific heat, but we do not have mass. And you can see that we are given the density of the solution, and if we know that the units for density are grams per milliliter, and we have 300 milliliters of solution, we can use dimensional analysis and just kind of turn that into grams of solution. So if we start with our given, which is the 300 milliliters of solution combined, times this density of solution over here, right? It's just like we want to put milliliters on the bottom to cancel that out just to end with grams. So it's going to be 1 milliliter per 1 gram. That's just the density of water, pretty much. These milliliters cancel, and then we're left with 300 grams of solution. So now we have everything we need to plug into Q equals MC delta T, which is going to be 300 times 4.184 times the temperature change of 27.1 final minus 25. 27.1 initial minus 25 final, which is equal to 27.1 minus 25, and we get that as an answer of 2635.92 joules, right? Because the units for the specific heat was joules per gram Celsius, and once the grams and the Celsius cancel out, we're just left with joules. And you got to be careful, because when we measure the temperature change of this, how it ended off at 27.1 and began at 25 Celsius, we actually like using a thermometer or something like that to measure the temperature change of the surroundings, not the actual reaction. So this is going to be equal to Q of surroundings. I'm just going to abbreviate that, SUR. And then we know that heat is not created or destroyed, it's only transferred. So we know that Q of the surroundings is going to be equal to the negative Q of the reaction. So divided by -1, we get Q of the reaction is just equal to negative 2635.92 joules. And then it wants the answer in kilojoules, and there's 1,000 joules in a kilojoule, so you just divide that by 1,000, and then you get negative 2.6 kilojoules, which is Entropy speed. Oh, I didn't see the extension. What is the molar enthalpy with respect to NaOH in kilojoules per mole for this reaction, given that 0.03 moles of NaOH reacted? So if we know that the units it even tells us right here the units are kilojoules per mole. So if we know that for when 0.03 moles of NaOH reacted, we got a release of energy of 2.6 kilojoules, we can just divide this number by, oh wait, hold on. Yeah, never mind. not dividing there. But okay, so since we know that that's the relationship, we can set this up as a kind of like an improper um, 1-to-1 ratio, and we can just do negative 2.6 kilojoules per 0.03 moles. And then when you actually divide that out, you'll just get the actual molar enthalpy, which is the amount of heat released per mole, which is going to be equal to negative 86.66 kilojoules per mole. Which there's no answer choice, but yeah, I'm pretty sure that's right. How much energy is released during the formation of 197 grams of iron according to the reaction below? All right, so this is kind of similar to the extension problem that we just had above, but the first thing you want to do when you're given grams and you have a chemical formula is, for the most part, just convert everything to moles. So if we convert these grams of iron to moles, we have 197 grams of iron. Remember, to convert to moles, you divide by molar mass. I think the molar mass of iron is 55.85 grams per 1 mole, which gives us 3.527 moles of iron. And so the question asks for how much energy is released. So if we set up the I guess the relationship between this, so we know that for every 2 moles of iron that are produced, this much heat is released, and we can set this up as negative 852 kilojoules per 2 moles iron, Fe. And we can multiply this by the amount of moles of iron we actually created. And it's just like the last couple of problems we've had. These cancel, and you're left with the amount of heat you actually released given the amount of moles of iron you created. And then when you multiply these two together, negative 852 times 3.527 divided by 2, right? Because there's still this 2 on the bottom. You get negative 1502.502 kilojoules of heat that were released, which that is going to be that's choice C, just not in scientific notation. Okay, use the standard reaction enthalpies given below to determine delta H reaction for the following reaction. This is going to be just Hess's law, rearrange equations, and yeah, just rearrange them to get what you want, which is right here. That's the goal formula. And the tip I give for these is just find some species in one of these, or in any of the equations that's only in that equation, and start with that first, because if you try to I don't know, try to balance for these oxygens first, it's just going to get really messy really quickly. So if we start with the first one, this one right here, this 4 moles of iron 4 oxide, iron 3, I don't know, I forgot. Iron 4 oxide, I think, yeah. If we start with that, we know that the only place in both of these equations where iron 4 oxide is right here. And it's on the products, and we want it on the reactants. So we can flip this to be, what is it, 2Fe3O4 creates 6Fe plus 4O2. But then also, if you look back at the goal equation, we want 4 moles of this, so we have to multiply both sides by 2, and then that gives us 4Fe3O4 creates 12Fe plus 8O2. So we've got the iron 4 oxide down. We don't need to change anything about the top equation, because that would change what we just worked for. And the only other, I guess, species that is only in one equation is this iron 3 oxide. And that's in this one. It's only in that one. And we want 6 moles of it, which in this equation we also have 6, so we don't need to change it. But it's also on the reactants, and we want it on the products, so we do have to flip the equation. So then we can flip this and we're left with 9O2 plus 12 Fe creates 6 Fe2O3. These 12 ions cancel from both sides, right? Because if they're on opposite sides, they cancel. If they're on the same side, they add. So let's cancel. There's 9 oxygens. Oh no. There's 9 oxygens on the reactants and 8 on the products. So 8 of these on the products cancel out, and you're left with just 1 O2. So then your overall reaction is going to be 4 Fe3O4 plus O2 creates 6 Fe2O3, which is exactly what we wanted from the Skoll equation. So because for this first reaction, reaction 1, we flipped it and doubled it, we're going to reverse the sign. So negative 1787 times negative 1 times 2 because we doubled it, and then the negative 1 on the front is because we flipped it. And then that's going to be equal to 3574 kilojoules. And then we flipped this equation 2, so that'll be negative 3946 kilojoules. So then whenever we add those two together, we get negative 372 kilojoules for this reaction right here, using Hess's law, and that is answer choice D. All right, given the data in the table below, determine delta H of reaction for the following reaction. These are pretty easy, just because they kind of give you all the data you need in the table. The only thing you need to worry about is forgetting to multiply by the stoichiometric coefficients, and I guess the order. So it's going to be products minus reactants for these. Yeah, and also don't mess up on the math because it gets kind of ugly. So the general, I guess, way to write this is going to be, that's a sigma sign, by the way, sorry. Delta H of, what is it? Delta H formation of the products times N for each product, because, right, we need to remember about the moles of each product per this reaction, minus delta H of formation for reactants, also times the moles of each one of those reactants. So if we consider this one, we have, if we consider this reaction, it's going to be 1 mole of silicon dioxide plus 4 moles of hydrochloric acid formed to create 1 mole of silicon tetrachloride and then 2 moles of water. So just like how we have up here, we need to start with products first. So then we have 1 mole of silicon tetrachloride and 2 moles of water. So we have 1 times negative 657.0 plus 2 times negative 241.8 minus, for the reactants now, there's 1 mole of silicon dioxide and 4 moles of hydrochloric acid. So 1 mole of that silicon dioxide times the delta H formation. That is not right. 10.9 plus 4 moles of hydrochloric acid, so it's 650, it's not 657. Negative 240, that's not that either, Jesus. Negative 92.3. And then we can write these out both individually for products and reactants. So it's going to be negative 657 minus 2 times 241.8. Oops. So we get negative 1140.6 minus, that's for the products, and then this next one will be for the reactants. It'll be negative 910.9 minus 4 times 92.3 you'll get minus negative 1280.1. Does that look fine? Right. Yeah, probably. Yeah, it's probably fine. These two negatives are going to make a positive, and then that will be, you'll get a positive 139.5 kilojoule reaction, which corresponds to answer choice B. Well, let me check that. Hope that's right. That's probably right. I'll let you guys know later if it's if it's wrong. Um, Consider the following phase transitions: sublimation, melting, condensation, freezing, evaporation, deposition. Select all from that list which are endothermic. And we know that endothermic means that we are going to, or that means, man, that was ugly. That means that delta H is going to be positive, right? Because endothermic means we're gaining heat. Exothermic would be losing heat, so it'd be negative. So, um, so just like right off the bat, you can think of these as like the states that are going up from solid, right? Because like I always think of water, that's the easiest way for me. So because these are endothermic, or we're looking for endothermic and it's gaining heat, you can think of like an ice cube. You need to heat it to melt it, and you need to heat water to vaporize it to turn it into water vapor. Um, so melting, or okay, let's look at sublimation first. Sublimation is going straight from solid to gas, right? Yeah, going straight from solid to gas. So if we know if we're going up the chain from solid to liquid to gas, if we're going straight to gas, we know that means it absorbed heat. So sublimation is for sure one of the ones that we want. Melting means I can think of this as like going from an ice cube to water. That's also going up. So we want melting. Condensation is. Hold on, wait, let me go back to that. Okay, freezing is going to be something like a liquid turning to a solid, so it's not freezing. Evaporation is going to be going from a liquid to a gas, so that's also absorbing heat. We want that one. Deposition is the opposite of sublimation, so it's going to go straight from gas to solid. So we don't want that one. So we can automatically cancel out anything that is freezing or deposition. So not A. Not this one. Evaporation is not even on this, or condensation, so we don't have to worry about that. Hold on, I'm freaking out right now. There's condensation. Okay, so condensation is going from from a gas to a liquid. Sorry for not knowing that. So we know that going from gas to liquid, something has to be cooled to go to gas, or to go from a gas to a liquid, like water vapor going to just water. So we also know it's not going to be condensation. So then we want sublimation, melting, and evaporation. And that's answer choice B. Yeah. Boiling wasn't even on this list, so I don't know what that is. Right? Did I miss that? Nah, we're good. But yeah. Cool. And again, boiling isn't endothermic. Wait, boiling is endothermic because you are going from from liquid to gas. Sorry, but it's not. It can't be B because it's not melting only. There are other things that are also are boiling only because there are other things that are also endothermic. Oops. Determine the flow of energy for the following chemical reaction. Um, the flow of energy. Okay, so if you see heat or kind of written in this format where it's like where it's kind of treated as a reactant or a product, um, that's just kind of like a huge indicator of what it's going to be. So if you see heat on the product side, you can think of this as like a reaction is occurring and heat is going to be released out as a product. And we know that when when heat is released, that's going to be exothermic, right? So we can automatically rule out D and A, and you can look at the second part about the energy relationship between the reactants and the products. Um, I guess two ways, in like a graph way or a qualitative way. So the qualitative way is like, if whenever you're forming products, you release heat, that means they are losing energy, which means they're actually more stable. It's kind of weird to think about, but another way to think about this is, I think you guys have had to do this on a couple of worksheets. But you have energy diagrams where you have like the reaction coordinate or the reaction progress, whatever, and then this is the potential energy of the reaction, and then so if the reactant starts somewhere here, they come a peak, and the products are lower, right? Because if we release heat, we're at a lower energy. Um, so yeah, that's kind of like another explanation. Um, so then that leaves us with the reagents are at a higher energy than the products, right? Because this height right here is higher than this height over here. So answer choice C. Which of the following systems gives off the most amount of heat to its surrounding when it cools by 15 Kelvin? Um, yeah, this looks like gives off the most amount of heat. This is a lot of work to do. Okay, so we're given heat capacities or specific heats. Um, I guess no, these are heat capacities because they're for a certain amount. Okay, so we know that if we're giving a heat capacity, we're going to use MC delta T, and we want the most amount of heat, which following gives off the most amount of heat. So yeah, we're just solving for Q. Um, so it gives us for copper, water, and ethanol. So we just want okay, sorry. It also tells us in the intro part that it cools by 15 Kelvin. So this delta T is going to be um, I guess a non-issue because it's going to be the same for all scenarios. So then we can say that Q is proportional to MC, not equal to, just we're just looking at relationships. So we know that this MC product is going to be directly proportional to Q, which means that when this increases, and if we want the most amount of heat released to surroundings, um, we just want the biggest product between these two. It's like the same one that we did a few problems ago. So then if we compare these first two, we want the largest product of MC, and we can automatically cross out B because they're with the same material, but A has more massive, or it is more massive. Um, and by that same logic, we can do the same thing for C and D. They're the same material, the same substance, water, but answer choice D just has more of it, so it's going to be a greater product, which means more heat change or more heat lost to surroundings. And then we just have to compare these products together. So Q is proportional. I'm going to do this for the copper first. So it's going to be 55 times 0.386. This is for water. Q is equal to 88 times 4.184. And this is for ethanol. Q is equal to 45 times 2.46. I mean, without even doing the math, you can kind of see what it's going to be. Water has the most mass and it has the largest heat capacity. So that means, oops, these are proportional signs. Um, that means that that system is going to give off the most heat to the surroundings. So yeah, so the answer is D. All right, which trends are correct for the energy of light? Um, this is just knowing the equation for the energy of a photon or a packet of energy. This is just going to be E is equal to H, Planck's constant, times C over lambda. And this comes from the C is equal to lambda v, which is just rearranged for v, which is nu, which is just the frequency of it. Um, and this right here is just replaced with that. So then which trends are correct for the energy of light? So if we're looking at this one for answer choice A, we see that energy is directly proportional to frequency. We see energy, frequency, and yes, they are directly proportional. There's no fraction bars separating them. See, energy is proportional to 1 over wavelength. We see in this one energy to 1 over wavelength right here. If you think this is like a 1 over wavelength, so that's also correct. And then if we look at answer choice C, energy is directly proportional to wavelength. We see that's not correct because it would have to be for this one, E is proportional to that, but in actuality we have E is proportional to 1 over that, so definitely not that. So then the answer choice is going to be D, which is A and B. Calculate the wavelength in nanometers of the blue light emitted by a mercury lamp with a frequency of 6.88 times 10 to the 14th hertz. This is going to be using this equation right here. This speed of light is equal to frequency times wavelength. So we want the wavelength. So if we're given this, C is equal to wavelength times frequency, we can rearrange this for wavelength and get wavelength is equal to C over frequency, which is equal to 2.998 times 10 to the 8th meters per second, divided by 6.88 times 10 to the 14th hertz, or hertz is equal to 1 over seconds. And that makes sense because if you put meters per second over 1 over second, you're just left with meters when we're looking at over here. And then that means that wavelength is going to be equal to I'll just abbreviate the speed of light with 3 times 10 to the 8th. We get that the wavelength is equal to 4.36 times 10 to the negative 7th meters. And then the question is asking for in nanometers. And honestly, you could just look at the answer choices right now and stop and just kind of see that B is going to be right. But if you want to know how to convert from meters to nanometers, so if we have our given 4.36 times 10 to the negative 7th meters, when we're converting to meters, we want to cancel out those meters, right? So 1 meter is times 10 to the negative 9th. Oops. Is 10 to the 9th nanometers, right? Because nanometers are really small, so that means there's going to be a lot of them in 1 meter. And that is going to be equal to, like you just probably could have guessed, 430 nanometers, which is answer choice B. One of the ultraviolet spectral lines emitted from a hydrogen lamp is found at 103 nanometers. What is the energy of a single photon from this transition? This is using the equation from 2 questions ago. The E is equal to HV is equal to HC over lambda. And for this one, we'll use this part of the relationship because we're given a wavelength, not a frequency, and it would just be extra work and redundant to convert back to frequency and use the other equation. So then we get that E is equal to Planck's constant H, which is 6.626 times 10 to the negative 34th times the speed of light. I'll just use the short form, 3 times 10 to the 8th, all divided by the wavelength. And remember, this is going to be in units of meters per second, so we want to convert this wavelength right here to meters. In, I guess, an easy way, just whatever whatever a wavelength is in nanometers, it's just that times 10 to the negative ninth in meters. So 103 times 10 to the negative ninth. And then that is going to be, it's going to be a long one. Fourth over 103 times 10 to the negative ninth, which is going to be 1.92 times 10 to the negative 18th, which is basically answer choice B. I just left out this extra 9 and they rounded up to 1.93. Pretty easy. What is true about the process of a match burning? The match is the system. So this is like another one of those things where you have to observe the surroundings and then you have to decide what the system is doing. So whenever you, let's try to draw a match real quick. It's gonna look horrible. So whenever the match is burning and you put your finger up to it, right? You're feeling the air, and the air is going to be hot, which means it has gained energy, it's gained heat. So that means the system, the match, has actually lost heat. So you can already cancel out C and D, because if Q is positive, that means the reaction, the match would gain energy or heat, but in this case, it's losing it. And then if Q is negative, losing heat, that's the same thing as exothermic, so the answer choice has to be B. BB. A sample of copper absorbs 43.6 kilojoules of heat, resulting in a temperature rise of 75 Celsius. Determine the mass of the copper sample. If the specific heat capacity of copper is 0.385 joules per gram Celsius. Okay, so the question is asking for mass, and we're given Q, delta T, and the specific heat capacity. So the only equation that we know right now is MC delta T, or Q is equal to that. And if we want the mass, we just isolate mass. So we get mass is equal to Q over C delta T. Okay, and then if we plug in some actual values, we have Q, and the problem it gives is that that it absorbs 43.6 kilojoules of heat. So that means that Q is going to be positive. If the sample of copper was losing heat, it would be negative, but it's absorbing, so it's gaining heat, it's positive. And then also the units for the specific heat are in joules, so we want to convert this right here to joules. So just multiply by 1,000. And that's like another, I guess, general thing about all these problems. Watch out for the units because we've had to convert a bunch of times, and that can kind of ruin a lot of things. So then we have this positive 43,600 joules of heat released or absorbed times the specific heat of 3.85 times the temperature rise of 75 Celsius. So if you think about temperature change, that's going to be temperature final minus temperature initial. So that means if the temperature rose 75 Celsius, that means this right here is going to be positive, and that means temperature final is going to be greater. So it'll be a positive 75. If it were the other way around, if it was like resulting in a temperature rise of, or a temperature decrease of 75 Celsius, that means that on this inside part of TF minus T initial, delta T would be negative, so that means this temperature initial would have to be greater than temperature final. But then once you plug all of that in, get 43,600 or 43,600.385 times 75. So then you get 1509.95 grams. But then the question again asks for mass in kilograms. So you just divide by 1,000. We should all know that. There's 1,000 grams in a kilogram. And I'm not going to write that out exactly, but that's basically answer choice A, 1.51 kilograms. Consider the chemical reaction and its enthalpy change. What is the enthalpy change of the related reaction? So this is kind of, I guess, like one of the Hess's law things that we did earlier when we flipped the reactions or doubled them. Um, but just much simpler. It just wants to know what happens to the delta H reaction whenever you just change one thing. We're not adding anything up. So if you look at this, it's A plus B gives you 2C. And then for the reaction that we're actually looking at, C is on the products. So that means we must have flipped it, right? And then also all the coefficients were halved. So on this one, it's 1, 1, 1, 1, 2, or 2. And then for this, the reaction we're looking at again, this 2 goes to 1. The 1 for A and B go to halves. So we know we halved the coefficients. So that means for this delta H reaction of negative 413, so we know that we flipped it, so we multiply it by negative 1, or just reverse the sign, and then we also halved it, so we have the reaction, and then that's going to be, I guess, about 207 kilojoules that were absorbed. How many moles of helium gas are contained in a 4-liter tank at 255 Celsius and 2.75 atmospheres? It seems kind of out of place considering all the problems we just had. But this is just like the beginning. You're given 3 variables: a volume, a temperature, and a pressure. And the one equation that we've been using this entire, I guess, quarter of the semester for this, in preparation for this exam, is the ideal gas law, nRT. And the question is asking for moles of helium gas, so we just, that implies, so we just move everything around to solve for n and isolate it. So we do n is equal to PV over RT is equal to a pressure of 2.75, a volume of 4, a universal gas constant of 0.08206. We're back to this one because we're using atmospheres of gas again. And then a temperature of 255 plus 273.15. Remember, always convert to Kelvin. For pretty much everything you do, you don't have to do it for calorimetry because you're just measuring a temperature change, but even then it's still good practice just to keep it in your mind to always use Kelvin because you'll use it for pretty much everything else. So then whenever we do these calculations, we get that there are 0.253 moles of helium gas, which it's kind of hard to see, but it's answer choice E right here. So yeah, easy. Consider 3 samples of gases, each of them at a temperature of 20 Celsius and a pressure of 1 atm. Which gas should occupy the smallest volume? And this is kind of another extension of the assumptions we make about ideal gases, that the gases occupy a negligible volume. So it actually doesn't matter for the same molar amount. It doesn't, like, the ideal gas laws, or the ideal gas law doesn't discriminate against which gas you're using because we assume that they're so small that it doesn't really matter. So they do actually all have the same volume, but we can look at the ideal gas law just to check it out. So we're looking at volume, so we want to solve for that. The volume is equal to nRT over, what are we doing, over P. All right, so we have the same moles in all these scenarios, so volume doesn't really affect anything. Or not volume, moles doesn't affect anything. R doesn't really affect anything, it's the same. They're all at the same temperature and they're all at the same pressure. And I'm not really canceling these out, but I'm just trying to show you guys that they don't really mean anything. And even this moles thing, it's not saying like moles of a heavy gas or moles of a light gas. Like, it's just moles of any gas, so it doesn't affect anything. So they'll all have the same volume. Pretty easy conceptual question. So if you just have those assumptions down, that should be a couple questions maybe on the test. that are just pretty easy. If a gas contains 0.35 moles of helium, 1.1 moles of neon, and 0.55 moles of O2, what is the mole fraction of neon, Ne, in that mixture? Um, yeah, these questions are kind of weird. This is way easier than the one we did at the beginning, but the mole fraction of neon, chi neon, is going to be equal to moles of neon. Oops, that was funky. Moles of neon over moles total, which is, so we know that there's 1.10 moles of neon over a total of 1.10 plus 0.55 plus 0.35, which is a mole ratio of 0.55, and that's answer choice D. And that makes sense though, because the mole fraction is just what percent um, of a certain substance makes up the entire thing, and if there's a total of 1.1 plus 0.55 plus that's around 2 moles. Actually, that is 2 moles. Is it? Yeah, that's 2 moles. And if there are 1.1 moles of neon, that's just over half, so that should be just over 55% of the total composition of gases. All right, last problem. A gas mixture consists of two gases which both contribute to the total pressure, 10 grams of helium, 10 grams of carbon dioxide. What is true concerning the pressures of the gases in this mixture? We can just, I guess, go by the answer choices and reason things out or not. The partial pressures of helium and carbon dioxide are equal since their masses are equal. Okay. The partial pressures of helium and carbon dioxide are equal since they are both ideal gases. The partial pressure of helium is larger than the partial pressure of carbon dioxide. And the partial pressure of carbon dioxide is larger than the partial pressure of helium. So, let's see. So if we look kind of a little bit back at the previous problem, I guess we can just restart. So earlier I wrote that the fraction or chi of anything is just going to be equal to the moles of that over the moles total is equal to the partial pressure of that over pressure total. Okay, and if we're looking at partial pressures, because that's what the problem is asking about, we can kind of look back at the ideal gas law if we want to see what the mixture of moles of gases is. So if we see PV equals nRT, we rearrange for moles, we get N is equal to PV over RT. That is not what we wanted. Hold on. We get the partial pressure is equal to nRT over V. And the only thing that's really going to affect the pressure of a gas is going to be the moles of that gas. So the partial pressures would be equal in the situation if we had 10 moles of helium and 10 moles of carbon dioxide, but we don't have that. We have 10 grams of each. So let's just see, if we convert this 10 grams of helium to moles of helium, we divide by the mole mass, which is 4.0026 grams per 1 mole. We get 2.49 moles of helium. And then if we do the same thing for, what's the other one, carbon dioxide, we have 10 grams of CO2 times the mole mass of that, which is, I think it's 44.001 grams per 1 mole, is equal to somewhere around 0.227. I don't know if this molar mass is 100% correct, because I'm trying to go quickly, but oh my goodness, bro, 0.227 moles of CO2. And we can right away see that these are not equal mole amounts. So they won't have equal partial pressures because if you look at this section of this formula, if you find the um, if you find chi of, let's say, CO2, it'll be um, CO2 is equal to 0.2227 over 0.227 plus 2.49, which is going to be a pretty small number. But if you look at chi of helium, you get 2.49 over 2.49 plus 0.227, which is going to be larger than this. Um, so you know that they don't have the same partial pressures. So you can automatically cancel out B and A. And then if we look at C and D, the partial pressure of helium is larger than the partial pressure of carbon dioxide. This answer choice makes sense because because you see, like, again, that the chi of this is equal to the partial pressure of a gas. And we know that if the chi for helium is much larger, then that also means that the partial pressure of helium is much larger than carbon dioxide in this scenario. So answer choice C. Good luck on the test in 2 days.